In question 1, part A, we're asked to find the equation of the altitude from P. So remember, that's the line that meets the opposite side of a right angle. It's the definition of altitude. So this is essentially a right angle in here. So we're going to find the gradient of Q to R and then flip that because it's a perpendicular gradient to get our gradient. So let's start with that gradient. So the gradient of Q to R. Just keep an eye on the diagram because you can see that it's got a negative slope. So it should be a negative answer that we get. So that's going to be 8 minus 3, just using the normal gradient formula, divided by minus 2 minus 13. Just keep an eye on the negatives because there's quite a lot of negatives kicking about in this question. So 8 minus 3 is 5 over minus 15. That'll simplify down to minus 1 over 3. And that looks about right because it's negative and it's quite shallow. So that's why it's a fractional gradient. So that's not the gradient we want the gradient that's perpendicular to that line. So perpendicular gradients, remember, they multiply together to make minus 1. So that means if this is minus 1/3 and the other one would have to be positive 3 over 1 or positive 3. So our gradient is positive 3 and that looks like a positive 3 gradient. Then we just need to use a point on our line. We've only got one point P, so make sure you don't plug in the wrong point. And we're just going to plug these into our normal straight line formula. So y minus b equals mx minus a. And then this sort of work through the algebra from there. So the b value is negative 1, so be careful with that because it's going to be y minus minus 1 equals the gradient 3x minus a, which is 5. And notice that there's no xy axis given in this diagram, so we can't quite easily check things like the y-intercept. We can sort of check it, but not as if we could if it was on an actual xy axis. So this will be 3x minus 15, and then just add in, subtracting 1 from both sides to get 3x minus 16. In part B of the question, they're asking us to find the angle that the line P to R would make with the positive direction of the x-axis. So that's the angle going this way. In other words, it's the angle in this side. So if you imagine the x-axis being something like this, and it's the angle in here, let's call that theta that we're trying to find, rather than the angle on the other side, which would be the angle in the negative direction of the x-axis. So this is part A, and then on to part B. So we're trying to work out this angle. We're going to use the gradient of that line to then turn it into the angle. So we need to work out a second gradient. This is going to be the gradient of the line P to R. So just using the normal gradient formula for this one. So we've got 2 points on our line. So 3 minus minus 1, just watch out because that's going to be a double negative, over 13 minus 5. So this gives us 4 over 8, which is 1 over 2. And again, just check that that gradient looks to be in the right place. So it's a positive gradient, so it should be going that way. And it's a fraction again, so it should be quite shallow, and that is quite shallow. So at this point, remembering there's a little formula that connects gradient and angle, so m equals tan theta. So we've got the m value already, the 1/2, so 1/2 can go in here, equals tan theta, and then to get the theta from there, we're just going to use the inverse. This is a calculator question, so inverse tan of 1/2 is not an exact value, so we'll need to put that in the calculator. So tan inverse of 1/2, and that comes out to be 26.6 degrees. And again, you can sort of check that on the diagram, so you can see that that angle is quite shallow, so it could be 26.6 degrees. In question 2, we're being asked to find the equation of a tangent line to this curve at the point where x equals 1. So ultimately, this is a straight line question, so we need to plug into our straight line formula. To do that, we're going to need a point and a gradient. We're going to get the gradient by taking the derivative, and we've already got half of the point. We just need to find the y coordinate. So I'm going to start by finding the gradient, which will come from the derivative. So starting by taking the derivative. These are in a differentiable form, so just using the power rule, that first term would differentiate to 10x to the power of 4, and then minus 3 for the second term. This is obviously a function, it's still got x's in it. To turn it into a number, which is what the gradient is, a numerical value, we just have to sub in the x-coordinate of the point we're interested in, which is x equals 1. So that means we can go straight to our gradient, which is going to be 10 times 1 to the power of 4 minus 3. So just plug it in there, and then we just need to calculate that. So 10 times 1 to the 4 is just 1, 10 times 1 is 10, minus 3 is 7. So that gives us a gradient of 7. There's no way to know whether that's accurate or not. We don't have a diagram, so we just have to trust that that gradient is fine. But to find the corresponding y coordinate that goes with this point, we just need to plug that into the original formula. So that's just going to be y equals 2 times 1 to the power of 5 minus 3 times 1. So it's quite convenient having a 1 because any power on a 1 still gives you a 1. So that's essentially just going to be a 2 times 1, 2, and then the second one's a 3, so it gives us 2 minus 3, which is minus 1. So that tells us the point we're working with is 1 minus 1. That's going to form our a and our b value when we put it into our straight line equation. So we've got all the bits we need now, so we can just go into the y minus b equals mx minus a. So another straight line equation question. There's heaps of these in higher and in these two papers. So y minus the b value, which is minus 1, that's going to be y minus minus 1, which will be y plus 1. Just to save a line of work in there, I'll go straight to the plus 1. Gradient is 7, x minus the a value, which is just 1. And then just working through the algebra, so expanding the bracket to get 7x minus 7, subtracting 1 from both sides, and we get y equals 7x minus 7 minus 1 is minus 8. So that's the equation of the tangent line to that curve for question 2. Question 3 is just a little 2-mark straight up trig integral. These can be a little fiddly because they don't quite directly match the formula sheet. The integral for cosine is on the formula sheet, but it's not quite in that format, is it? So it can be a little bit confusing. The one thing to take from the formula sheet, when you integrate cosine, you get positive sign. When it's a derivative, it's negative sign. So it's going to be a positive sign. The brackets never change in these, so essentially we're changing the cosine to a sine. The bracket doesn't change. The 4 in this case is playing the role of what would be the a value in the formula sheet. But that a value in the formula sheet, the 1 over a, that a is a derivative. Even though it's an integral, it's a derivative of the inside of the bracket. The inside of this bracket, 4x plus pi by 3, is still just 4 because pi by 3 is just a number. And if you differentiate a number, you get 0. So the derivative of this is 4, so that means we're dividing by that. And the 7 is just a constant, so we can just leave the 7 there, and we can write our answer as either 7 over 4 sine of that bracket, or you could write 7 sine the bracket, all of that over 4. It doesn't really matter which way you write that, but you do need a plus c on the end because it is an indefinite integral. So just one line of work in for that question, question number 3. Question 4 is our graph transformation question. They're giving us this graph, which is f of x, and they want us to sketch the graph of the transformation of that function, so 2f of minus x. Slightly awkward one this, because of the minus x, you don't see that very often at higher. A lot of students are going to miss what that does to the graph. The 2 is quite normal to see a number in front, but the minus x in the bracket actually reflects a graph in the y-axis, so it's like a mirror image of the graph in the y-axis. Essentially what that means is that all the x coordinates of these key points are going to become the negative of themselves, or the opposite sign. So for example, the point at 2 is going to get reflected over to minus 2. But all of these graph transformation sketch questions are not really about the sketch. The sketch is trivial. The question is about transforming the point. So let's not worry about the sketch, that'll take care of itself. Let's worry about the point. So we've been given 3 points. Remember, these are not the full coordinates of the points. You need to write the full coordinates. So this point is minus 1, 0, not just minus 1. This other root point is at 2, 0. And the final point is at 0, minus 2. That's the y-intercept. So what we want to do is to transform these points. In other words, to figure out where those points get moved to on the new graph. Then we can plot them and then just draw in the graph. Drawing in the graph is easy. So this part is just making new coordinates. So this is where you've got to think about the graph transformation, the position of the numbers, and just what they've done to the function basically. So if it's in the bracket with the x, that does something to the x coordinates. If it's not in the bracket with the x, so like a number here or a number on the end, that affects the y coordinates. So this 2 in front, which is the only thing outside the bracket, that's the only change to the y coordinates, and that just multiplies them by 2. That's stretching the graph vertically, kind of like if you take a sine or a cosine and you make it 2 sine x or 2 cos x, it stretches the graph. So that means that our y coordinates are going to get doubled. So if you double 0, you still get 0, the same for the other one. If you double minus 2, multiplying it by 2, you get minus 4. The minus x, like I explained a moment ago, is a little bit tricky. You probably haven't seen that very often. It does make the x coordinates the negative of what they were. So the one which is at -1, minus minus 1 becomes 1, minus of 2 becomes -2. This one's at 0, -0 is still 0. So essentially these are the transform points. These are the ones that are going to be on the new graph. So I'm just going to go ahead and plot those. So I'll start with this one, the y-intercept. Ideally, it's best to have this on the same graph because then you can see the change. So -4 would actually be like way down here. So I'll maybe just draw that a little bit longer actually. So -4 might be down here somewhere. Okay, and then this guy is at -2 on the x-axis. So that's going to be like a root point up here at -2. This guy is now at 1 on the positive side, so that's going to be over there at 1. And if you think about the mirror image of the graph, like if that was reflected around the way, then it's going to be a similar sort of shape of graph, but just round the other way. So this point, which is at -1, is still going to be like a root point, but the graph's going to be sort of coming down this way, and this point's still going to be a turning point, but the graph's going to be going up this way. So it's just like a mirror image of itself. But these points still retain the same features. There's still the y-intercept and 2 root points, and this guy's still going to be a turning point. So in terms of drawing the graph, let me just move my -2 to get it out of the way up to here. In terms of drawing the graph, it's going to basically go up something like this, turn on that point. It's going to come down through that y-intercept point, which it turns on, and then it's just going to go up through that point because it goes through that point on the original graph. So that's the transformed graph 2f of -x. In question 5, we're given this function f of x and we're asked to find a rate of change when x equals 4. The challenge with this question is the interpretation, like what does rate of change mean? You should technically know that that is just code for derivative. So rate of change, derivative, essentially the same thing. Still not easy because you still need to know how to differentiate this function. It's in the form to use the chain rule. So interpretation is the first thing, knowing that we're differentiating. Once we differentiate, we're just going to sub in the 4 later on. So thinking about how to take the derivative of this function, it is a chain rule like I said. So bring the power in front, just leave the bracket alone. Reduce the power by 1, just like normal differentiation. But the thing that makes it the chain rule in all of the different versions of the chain rule is multiplying this by the derivative of the inside of the bracket. The derivative of that expression there is -2, so got to get the negative. And we're almost done at that point. We can just multiply the 4 and the -2 together to tidy up. So it's going to be -8 bracket 3 minus 2x to the power of 3. So that gives us our rate of change or our derivative. We just need to evaluate it at 4. So you can just sub in the 4, so make it f-4. Or you could write when x equals 4, and literally just a bit of numeracy now. So putting in the 4 carefully, so it's going to be 2 times 4 inside the bracket. This one is a calculator paper, so you could theoretically do this on the calculator if you need to. So just quickly checking this. So this is going to be 3 minus 8, which is -5 cubed. So you can see why they put this in the calculator paper. The numeracy is a little bit awkward. That's going to be -8 times -5 cubed, -5 times -5 times -5. That's going to be -125. When you multiply these together, you're going to get a double negative, a positive, and I think they multiply together to give us 1000. So slightly weird, big looking answer, but the fact that it came out to be a whole number, like a nice round number, 1000, not like some weird number, kind of suggests it's probably right. And I think that is right actually for that question. So f-4, rate of change at x equals 4, 1000. Okay, so the next question is to ask us for the inverse of this f of x function. So standard technique here is to change the f notation, the function notation, to a y, and that's just because we're going to do some algebra on this. Some students will then swap the x and the y at this point. You can do that. It doesn't really matter if you swap them or not. But the goal, regardless of which way you do it, is to change the subject of the formula to x, the other variable, and that will then give you the inverse. So how you go about the algebra is up to you because there's a little bit of personal preference, but probably the smartest first move here would be to get rid of the 3, to move the 3 away from the x term. Remember, we're trying to make x the subject, so we're moving things away from the x. The thing that makes this one more difficult than some other questions of this type in past exam papers is having the variable on the denominator. That definitely does make it a little fiddly. So if you multiply both sides by x, that will get rid of that fraction. so that there's no longer a denominator, and that would give us this here. And then keep in mind we're trying to make x a subject, so we need to divide the y minus 3 to the other side. So we're going to end up with x equals 2 over y minus 3. So that, remember, gives you now the structure of the inverse function. So that will tell us that we can just rewrite our original function notation with the minus 1. So f to the minus 1, the inverse of f as, remember, put it back as an x, so it's 2 over x minus 3. Question 7 is a very standard trigonometric equation. So typical setup, it's got a mix of a double angle term cos 2x and a single angle term. That means we need to swap out the double angle term using the formula sheet. Notice also the range of values, 0 to 360, so that tells us we're working in degrees, and also that's the allowed range of our solutions. Notice they've knocked off 360, so you wouldn't be allowed to include 360 if that was a potential solution. So first thing here is either to bring this term over to the left, because we need to make the equation equal to 0, or substituting from the formula sheet. It doesn't really matter which one you do first. I'm just going to leave it on the right. But be careful with the substitution. So two things. One, you've got to get the right formula, which in this case has to match up the other term, which is a sine term, which will be the 1 minus 2 sine squared x, but also this coefficient of 3 has to multiply to that substitution. So good practice here is just to put that in a bracket. So 3 bracket 1 minus 2 sine squared x, and that's really just to make sure that 3 ends up multiplying to both parts of that expression. So the left hand side we're just going to keep the same, sine x plus 2, multiplying out the bracket to get a 3 minus sine squared x. Remember, this is now essentially a quadratic trigonometric equation, so we need to get all the terms on one side. You want to put the highest power term first, so I'm going to start by moving the negative 6 sine squared to the left, which will make it a positive 6 sine squared x. That's playing the role of what would normally be like an x squared term. The sine x is playing the role of what would normally be an x term, so we'll put that one next. That's a positive sine x. And then just pulling the numbers together, so 2 on this side, 3 on that side is going to become a minus 3 on the other side, so 2 minus 3 would be minus 1. So at that point, we've made our substitution, we've set it up as a quadratic trigonometric equation. This is normally the tricky part, factorizing. This one's not too bad because it's got a 1 on the end, so the only two numbers that will make 1 when you multiply them are 1 and 1. So not the worst one ever. Still a wee bit tricky with a 6 though, because it could be a 6 and a 1 either way, or a 3 and a 2 either way. But you can definitely put in the 1 and the 1. The challenge is really trying to make the 1 sine x in the middle. I think in this case we're going to need a 3 sine x here and a 2 sine x here, so they would multiply to give you the 6 sine squared. These are going to multiply, we need to make them multiply to a minus 1, and I think in this case, because we're trying to make a positive in the middle, we need to make this one positive and this one negative. So quickly check that. If you multiply those, you get that. If you multiply those, you get that. If you multiply those, you get minus 2 sine. If you multiply those, you get 3 sine. So minus 2 plus 3 gives you the 1 sine. So that part is quite challenging, but that is the two factors. Then just splitting these off into two mini equations. So we're going to get 3 sine x minus 1 equals 0, and then 2 sine x plus 1 equals 0. So now is when the kind of proper trigonometry part kicks in. So just start by rearranging these equations. So in this one, we're going to get sine x equals 1/3. Remember, this is a calculator paper, and these are not, or this is not an exact value. So we need to use the inverse for that one. So sine inverse of 1/3. We also really should use a CAST diagram as well to check our solution. So I did this one earlier, and this comes out to be 19.5 degrees, I think. I'll just check my cheat sheet. Yes, 19.5 degrees. So that might be the first solution, but we do need to kind of check that on the CAST diagram. I'll just put a CAST diagram over here. So in this case, for the first equation, we might need one for this one also. For the first one, we're dealing with sine function and a positive value, so we're checking the first and the second quadrant. So that solution 19.5 is in the first quadrant, so we can keep that as a solution. Second one is in the sine quadrant, so that's the 180 minus quadrant, remember? So 180 minus our first solution. So that tells us our second solution would be 180 minus 19.5, which is 160.5, I believe. So they're both solutions, so you can assign them to x at this point. So x equals 19.5 degrees and 160.5 degrees. Remember, you need to get degrees in there as well to get the marks. Still need to develop the second one, so just going down a similar kind of thought process, we get sine x equals negative 1/2. This one is a little bit trickier because of the negative. This is an exact value, so you could theoretically do it non-calc, but it's a calculator question if you can't remember the exact value. So this will be sine inverse, remember, of just 1/2. You don't put the negative into the inverse. So that's going to give us 30 degrees from exact values, or from the calculator, if that's how you did it. Then we need to check a cast diagram, a different, separate cast diagram for this one. So this time we're dealing with sine negative, so basically it'll be the other two quadrants, so not here and here, but here and here. So we need for this quadrant 180 plus, in this quadrant, the fourth quadrant, 360 minus. So 180 plus our 30 to give us 210 degrees, and then 360 minus 30 to give us 330 degrees. And if we look at our solutions, these two and then these two, they all lie within the correct range, so there's nothing to do with knocking solutions off. These are both valid solutions, so we can write those down as x as well. So x equals 210 degrees and 330 degrees. So 4 solutions in this question: 19.5 degrees, 160.5, 210 degrees, and 330 degrees. In question 8, we're being asked to calculate the shaded area. So essentially it's the area between two curves, between this curve and, well, technically a straight line. So between the curve and the line. I've not replicated the diagram here, but remember the key with this technique is to identify the upper function and the lower function, and the formula, if you like, is the integral of the upper minus the lower function. So from the diagram, you can see that on the shaded area, the upper function is the curve, and the lower part of the shaded area is bounded by the line. So this is our upper and this is our lower. So we just need to plug those into the formula to get going. So it's going to be the integral between the limits. The limits are the points of intersection of the two functions graphs on that shaded area. They're given in the question as -2 and 1, so quite generous because you don't need to work those out like you normally do, or at least sometimes do. So remember your lower limit, the smallest number goes here, and then 1 would be the upper limit. So we're going to put in our upper function first, which is the cubic function. So x cubed minus 2x squared minus 4x plus 1. Good practice, remember, use a bracket for both of these because we're subtracting, particularly for the second function, which is x minus 5. And that's just to avoid missing double negatives and things like that. So you'll probably get a mark already just by populating that sort of formula and setting it up. Now we need to evaluate that integral. This one is a little bit messy in terms of the numeracy, but it is calculator, which is so it's quite common to get difficult numeracy in a question like this if you can use the calculator. So you could integrate all of these terms, but to save having to integrate 6 terms, we can merge these two back into this one. Then we've got fewer terms to integrate and also fewer terms to calculate with later on in the numeracy part. So before we integrate, we'll just fix those by simplifying. Just keep your integral sign at this point. Remember as well, you need your dx on the end, so we're not integrating yet, so we don't want to drop the sign. So x cubed, there's only one of those, so we can't do anything with that. Same with the x squared term. This x term, minus 4x, we can take away the other x, so it's going to give us minus 5x. And then the 1 minus minus 5, so that's a double negative, that'll be 1 plus 5, to give us a 6 on the end. Okay, so that's the terms. The terms are now fully simplified. These are all in an integratable form, so we can just go ahead and integrate using the power rule. Remember, because it's a definite integral, we need to put the result of this integration in a square bracket. So just a normal power rule, so increasing the power by 1, dividing by the new power. Second one will be 2x cubed over 3. Next one will be 5x squared over 2. And then the 6, remember, a constant integrates to the constant times x, so 6x for that one. And then just moving our limits over to the right-hand side. So you would get another mark for correctly integrating. The rest of the marks are really just for the numeracy. It is quite messy. There's a bunch of terms. They're quite ugly. None of these simplify down either. Sometimes the fractions will simplify down. So you've just got to start crunching the numbers. So if you put in the upper limit first, remember, so we're just putting that limit into this expression. So we're going to get 1 to the power of 4 over 4. 2 times 1 to the power of 3 over 3. Probably don't really need a bracket there, to be honest. minus 5 times 1 to the power of 2 over 2 plus 6 times 1. And then we're going to repeat that with the minus 2 limit subbed in. We've kind of run out of space there, so I'm just going to put it here. So I'll be subtracting from that the minus 2 subbed in. So it'll be minus 2 to the power of 4 over 4. Just be really careful with the numeracy, minus 2 cubed. And then really after this line, it's just a sort of calculator exercise. Probably a little bit too much to put all of that in the calculator in one go. So however you choose to do it, maybe putting that in one go and then that in as a separate bit of working and then pulling those together, something like that. But whatever way you do it, make sure you do it carefully. So just to save a bit of time, I'm not going to go ahead and crunch all of these numbers. I did this earlier and we'll refer to my cheat sheet. So it came out to be 367 over 6. So 367 over 6, or you could make that into a decimal number. It just depends how you've done the calculation. I think either would be acceptable, either this or the decimal version. I don't think that simplifies down. And remember, because we're working in a shaded area, it's unit squared or square units. And that's the final answer for that one. Question 9 is just a typical wave function question. So one of the most predictable questions at higher. The part A is very standard. Part B, which we'll get to in a moment, is more challenging. They vary year on year. We'll need a result from part A to tackle part B, so we'll get to that in a moment. So remember that this is really just an application of the addition formulas. So trying to turn this expression 7 cos x minus 3 sin x into this, which essentially means finding the k and the a values. So the first move with this question, there's different ways to lay it out, but the first move will be to expand the sine x plus a according to the formula sheet. So just be really careful with the expansions because it's easy to get something in the wrong place. Remember, the formula sheet is in capital A and capital B, so our x and a are playing the role of what is a and b on the formula sheet. So this is going to expand as k sine x cos a. For the sine expansion, the plus stays as a plus. Remember, you also need to carry that k into the second term, and then this would be cos x sine a. Okay, so there's no magic in that, it's just literally copying it off the formula sheet. Good practice to then spin these around, put the x term second. You don't have to do that, but that's just for algebraic reasons, because normally the variable, the x, goes second, or third in this case, but it goes on the end. So just spinning those around in both parts of the expression. Look, messed that one up. Should be the other way around, so it's going to be k sine a cos x. Okay, and you can just pull the left-hand side down if you wish. It doesn't really matter if you pull it down or not, but it's probably good practice to do that. So however you set this question up, at some point you should have something that looks a little bit like that or some variation on that. But it's really the next part that can be a little bit tricky. So we're matching up the left and the right-hand side to make two little mini equations. So on the left-hand side, the thing that goes with the cos x is 7. On the right-hand side, the thing that goes with the cos x is k sine a. So we're making the little formula, if you like, the little equation that k sine a is equal to 7. Similarly, matching up the sine x, we've got a minus 3, so we know that's going to be equal to minus 3, and the sine x on the other side goes with k cos a. So it's really just a game of matching up by inspection the left and the right-hand side parts of the equation. So that's going to be a positive k cos a. So it's from these two little mini equations that we're going to get our k value and eventually our a value. So the k value is probably well, it's the one that we normally do first, but you can do them in either order because they're not directly dependent on each other. So the k value is just based on Pythagoras. In fact, it is directly Pythagoras, but it's just these numbers basically squared and then added together and then square rooted. So we just got to know that formula, essentially, just simplifying this. So that would be 49 plus 9, that's a wee bit too big, and then that would finally simplify to root 58. So it's not unusual to get a root number for the k value. In fact, probably more of them are root numbers, like surd type numbers, than they are whole numbers. So that's perfectly fine. I think that is correct for this one. The a value, remember, we're going to get by making a little formula, by dividing the sine equation by the cos equation. If you divide sine by cos, you get tan. So we're going to get tan a equals the sine number divided by the cos number. So it's going to be 7 over minus 3, like this. So this is essentially a trig equation to solve. This is a calculator question, it's in degrees, we've got to be aware of all of that stuff. And we do need to think about the CAST diagram in this question anyway, but particularly if there's a negative kicking about. But just think of this as a normal trig equation. So in a normal trig equation at this point, you would take the inverse, but you would drop the negative like this. I did this one earlier, it comes out to be 66.8 degrees, I believe. I'll just check, consult my cheat sheet. Yes, that is correct. So that's not our A value because we need to make an adjustment on the CAST diagram. Remember, your CAST diagram for this wave function question is not based on this equation directly, it's based on these two. So that means we're going to end up with 4 ticks on the CAST diagram. So sine positive, that's going to be a tick here and here. Cosine negative, cosine positive would be there and there. So negative is going to be here and here. Wherever you've got a double tick, that's the quadrant where the A value is going to be. So in our case, the second quadrant. Second quadrant is 180 minus. So that tells us that our A value will be 180 minus 66.8. And that is 100 and, did I check this? Yeah, 113.2, that's right. So 113.2 degrees for A value. So what does that tell us? Well, that tells us that this guy here is equal to the K value, root 58, sine x plus the A value, which is 113.2. And it's maybe good practice just to write that somewhere, running out of space here, but I'll write it at the bottom. So it'll be 7 cos x minus 3 sine x is equal to root 58. So I'm just plugging in the K value there, sine x plus 113.2 degrees. So that's the first part of the wave function question. Moving on to the second part. In the second part, they're not giving us this expression, they're giving us this expression, and they're asking us to find the maximum value, and then in the second part of the question, to find the x value where that occurs. There's always a link between the first part and the second part, so it's quite easy to see that to get this, they've just taken this guy multiplied by 2. So maybe just starting by saying, well, this is just 2 times this guy here. So it's 2 times 7 cos x minus 3 sin x. Often in these part Bs, they do directly match this up with this, so you can see directly the link, but it's not uncommon to get some multiple of them. But we know from the first part of the question that this guy here can now be written in this form here. So that's going to be 2 times root 58 sine x plus 113.2. Okay, so that's where we're pulling in our result from part A, and that's always going to happen in the part B. So now we can actually get to the question. The question is, what is the maximum value of that function? Well, the maximum value is just the highest point on the graph. Now, I don't know what the graph of that looks like, but I do know what the graph of that looks like because it's just a single trig function, a sine function, and this is just a graph transformation of the sine function. So if you think about what a normal sine graph looks like, normal sine graph goes something like this. We're dealing with the maximum value in this question. This is normally the maximum value here, isn't it? Which is normally 1. But this value here, the 2 root 58, that is the amplitude value. That's going to stretch the graph of that sine function. So a normal sine function goes to 1 and down to -1, but having this number in front, this number has nothing to do with the maximum value, but this one does affect it by stretching the graph. So on that graph, this point would be at 2 root 58, which granted is a kind of weird number, and this would be -2 root 58. So that highest point on this graph would be 2 root 58. So therefore, the maximum value is 2 root 58. Just like if you had the graph 2 sin x or 2 cos x, the maximum value would be 2 and the minimum value would be -2. It's the same idea here, just a slightly trickier number. Second part of the question is arguably more demanding because they're asking for the x value where that maximum value occurs between 0 and 360. So going back to a normal sine graph, y equals sin x, that point occurs at 90 degrees, or in radians it would be pi over 2. So 90 degrees, we need to think, okay, if it's normally at 90, where would it be with this graph transformation? Well, this graph transformation, remember, a plus in the bracket moves the graph to the left, not to the right. So that point, which is at 90, we're actually going to have to subtract from that 113.2. But when we do that, obviously that's going to go into the negatives. Now, the question says that we've got to find the x value between 0 and 360, so we're not allowed the actual answer to this. But if you remember at this point the periodic nature of a sine and cosine graph, every point recurs every 360 degrees on a normal sine and cosine graph. So this will give us an answer like over here somewhere, which we're not allowed. But if we then add 360 to that, we'll get back to the answers that we are allowed. So you could set it up like this and then add on the 360, or you could work that out and then realize that's negative and add on the 360. Either way, it's going to give you the correct answer, but it is a tricky one, that, because it's pulling this into the negative part, where the answer would be valid, but it's not valid in this particular question because it's between 0 and 360. This is going to move us back into that range, and that came out to be, I checked this one earlier, 336 degrees. Yeah, 336 degrees. So yeah, quite demanding, that particular part of the second part B of that wave function question. Question 10 is to determine the range of values for which this function is strictly decreasing. So first of all, notice in the question it's worded range of values, so rather than being x equals something, it'll be x bigger than something or less than something or between two limits. That's the first thing. Second thing, strictly decreasing, what does that mean? Well, either that the derivative is negative or that the graph is sloping down. Those essentially mean the same thing, but two different ways to go about the question. So you could either do it by seeing the graph of the function, so essentially making a mini sketch, for example, using a nature table, or you can just take the derivative and set that less than 0 and sort of turn it into a quadratic inequation. I'm going to do the first way, but either way is fine. So in either case, we need to take the derivative because where a function is decreasing or increasing is really dictated by the derivative, which is essentially the gradient. So just using the power rule, these are all in differentiable forms. So using the power rule to get 6x squared and plus 18x minus 24. I'm going to go ahead and find the stationary points to allow me to then draw a mini sketch of the graph, and then that can allow us to determine where it's decreasing or increasing. But in this case, we only care about the decreasing. So writing in something like for the stationary points or at the stationary points, the derivative f dash x equals 0, and then just going ahead and setting that trinomial equal to 0 and then trying to solve that. So if you've done this part correct, you should find that this trinomial factorizes. This one has got a common factor of 6, so we could either pull that out, or better still, just divide everything by 6 to make this easier to factorize. So that would be x squared plus 3x minus 4 equals 0. And if this does not factorize and it tells you you've basically done it wrong up to this point, it should really factorize. Or if it does factorize, you've probably done it right. So this one's a trinomial. It's going to need two brackets like this. So we'll need an x and an x and a 4 and a 1. And we'll need a plus 4 minus 1. So these would multiply to give you minus 4. But plus 4 minus 1 gives you the plus 3 in the middle. So splitting these off into two little mini equations, we get x plus 4 equals 0. And we get x minus 1 equals 0. These are just little linear equations. So simple to solve to get minus 4 as the first solution, and then to get 1 as the second solution. So the way that I'm going to go about this from this point is just to draw a quick nature table. A nature table, remember, is essentially a mini sketch of the graph. And you can do these quite quickly. It seems like quite a long process, but it shouldn't really be all that long. So I'm just going to put it all on one nature table, because if you want to see the full sort of spectrum of how the graph looks, so putting in your two stationary points, so minus 4, 1, remember these have to be in numerical order. Choosing smart numbers between these, I'm going to put a 0 in there. I'm going to choose a minus 10 and a 10, just because they're easy numbers to calculate with. On the next row, we need the derivative, f dash x, and then the final row is the slope or the shape, whichever way you want to call it, so the shape or the slope. That's going to be where we essentially draw a mini sketch of the graph. So at the stationary points, remember the derivative is 0, so you can put those in. Using a 0 is a good call for a polynomial function because they're easy to calculate with. So if you look at the derivative and put a 0 in there, it's going to be 0, 0 minus 24. That's minus, negative, that's all we care about. We don't need the actual number, just whether it's positive or negative. And then if you put the 10 in here, you would get 60 times 6 is 600. You would get 100 times 6 is 600, plus another 180. It's going to be like super positive, so easy to identify that as being positive. Using the minus 10 means you're going to get a similar result, well, the same result for the first part, because when you square negative 10, you get the same result, 100, so that's going to be 600. That one would be negative, but the 600 dominates the expression, so that's definitely still going to be positive. So I've gone through that quite quickly. You could check that, but those are correct. And generally in a cubic function, the signs will alternate because the graph kind of goes up, then down, then up, or the other way around. So you're looking for that alternation. And in fact, if you know that it's a cubic function and you know it alternates, you can essentially cheat the nature table, because if that's a minus, then these kind of have to be pluses for most cubic functions. So that means our graph's going to go like this, and then like this, and then like this, and then that, and like that. Remember, these two horizontal lines are not actually lines, they're just one single point, the stationary point. So in reality, this graph would go like this. A curve, it's not actually a stick diagram, it's a curve. So these are our 2 points here at -4 and 1. Going back to the question, which asked where is the function strictly decreasing, it's decreasing here in this part of the graph. Like that's the part where the derivative or the gradient is negative. Conversely, it's increasing here and increasing here. So we only care about this part, but that's the part between the two stationary points. That's the part where the x values are between -4, so bigger than -4, and 1, so less than -1. So that's the final range of values that we're looking for. In question 11, part A, we're asked to find the distance between the center points of the two circles, C1 and C2. So to achieve that, we first of all need to find the center points, and then we can use the distance formula. The two circles are given in the different circle equation formats. The first one is a basic one, the second one is a general one. Different methods for finding the center point. So for circle C1, these numbers essentially give you the center point. Just got to remember that the formula is x minus a and y minus b, so that means the first one would just be a 4, but the second one would have to be a -2. So it's just a little bit of interpretation there of the formula sheet. And then for the circle C2, maybe got to work a wee bit harder. This is the one that's got the g's and the f's and the 2g's and all that stuff. But essentially the center point is just these two numbers halved and taken the opposite sign. So that term there, the 2, on the formula that represents 2g, and the center point's x-coordinate is -g. So that really means you're just halving the number and taking the opposite sign, taking the negative of it. So just by looking at that, half of that is 1, take the negative of that. So it's going to be -1, half of that is -3, take the negative of that, and that is 3, just like that. Okay, so we need to work out the distance between those. That means we need to use the dreaded distance formula, which a lot of students struggle to remember. It is just Pythagoras, essentially. It's finding the long side of a right angle triangle. The formula itself is x2 minus x1 squared plus y2 minus y1 squared. Just the difference between the x-coordinate squared plus the difference between the y-coordinate squared and then square rooted. So if I sort of assign this to be x1, y1, and this guy to be x2, y2, then we can just start plugging in our numbers. So x2 for me is -1, so it's going to be -1 minus 4 squared, and then y2 is 3, so it's 3 minus -2, which is 3 plus 2 squared, and then we're going to have to square root all of that. These numbers look quite nice because that's -5 squared, which is 25. That's 5 squared, which is 25. So adding those together, that would be the square root of 50. That's going to simplify using surge, so that becomes root 25 root 2. Square root of 25 is 5, so that becomes 5 root 2. So 5 root 2 is the answer for part A. That's the distance between the two center points. The second part of the question is asking us to work or to show that the circles overlap at 2 points. So we're trying to show that we've got a scenario, something like this. So there's 2 points of intersection between the circles. They're kind of guiding you through. I mean, that is a standard technique, but it's not that often it comes up on final exams, although it is in the course. but they're kind of guiding us through because they've made us work out the distance between the two center points like this. So that distance there has come out to be 5 root 2. The way we're going to show that there's 2 points of intersection is to work out the radii, so the radius of each circle, add those together and then compare it to this number here. And if it turns out that if you add your 2 radii together, and the sum of those radii is greater than this number here, then that must mean that the 2 circles overlap at 2 points. So you've got to kind of think about the logic of that a wee bit. But the first challenge in this part, second part B of this question, is to find the 2 radii. In the basic circle equation, this number is a radius squared, so we can just work out the radius of circle C1. So I'll maybe call that R1. That's just going to be directly root 37, so no magic with that one, you can just pick that off the formula sheet. For C2, because it's given in the general format, it's a little bit tougher. This is the square root of g squared plus f squared minus c. It is on the formula sheet. Remember, that is our 2g and that is our 2f, so we need to half those numbers, so it's going to be the square root of, not 2 squared, but 1 squared plus this one, minus 3 squared, minus the c value, that's the c value, it's already negative, so it'll be minus 7, so plus 7. So just tidying that up, that's going to be the square root of 1 plus 9 is 10, plus 7 is 17, so it's going to be root 17. So our 2 radii are root 37 and root 17. We want to add those together, so radius 1 plus radius 2, so that's root 37 plus root 17. I checked this earlier on the calculator and it came out to be 10.2 approximately. This number here, 5 root 2, that number is approximately 7.07. So what we've proven is that the sum of the 2 radii, this here, 10.2, is greater than 7.07. So in other words, the sum of the 2 radii is greater than the distance between the 2 centers. So you would need maybe some kind of sentence to say why that then implies that they overlap at 2 points. But that is basically the logic. Just some kind of statement implying that that scenario there leads to that scenario there. Question 12 is a differential equation. Not always easy to recognize, but it is the only question that starts with a derivative. It's very tempting if you see the derivative to differentiate, but actually we want to undo the derivative to get back to the original function, so that means we need to integrate, the opposite of differentiation. So we're going to set this one up as an integral. The numbers given, the point, these are the initial conditions. Later on there for finding the c value in our function, so after we integrate. So we're going to set this up just as a normal integral. There's no limits in this case. It's tempting as well to make those into the limits, but it's just an indefinite integral. So the integral of 8x cubed plus 3, remember your dx on the end. So both of those terms are integratable by the power rule, so we can go straight into the integration. Don't need a bracket because it's an indefinite integral. We will need a plus c on the end. So increasing the power by 1 and dividing by the new power. Remember that a constant, like a 3, integrates to 3x, and then just put in our c on the end like that. So we can tidy this up, in this case, by dividing this one top and bottom by 4. So we're going to get 2x to the 4 plus 3x plus c. So just by interpretation for that question, you're probably going to get a mark already for knowing what to do. But what have we done? Well, we've taken the derivative and we've integrated it. So our integral is an antiderivative, so it undoes the derivative. That means that what we've got at this point is our y function. The only thing we need to do is to find the c value just by plugging in these initial conditions. These are the x and the y coordinates, so we can put the 3 in the place of the y. We can put the minus 1 in the place of the x's. There's 2 x's, so minus 1 in here as well. And all we're doing here is to try and figure out numerically the c value. So we'll just keep that one as 3 minus 1 to the power of 4. That's kind of like minus 1 squared. That's going to be just a positive 1 times 2 is 2. This guy would be minus 3 plus c. So we get 3 equals minus 1 plus c. So it tells us the c value is 4. So all we need to do at this point, now that we've got the c value, is go back to this line and just write essentially our final answer, our final function, the function including the new c value. So the final answer for this one would just be y equals, and it's y in this case because the derivative was given as dy dx, If it was given as f dash x, then this would be f of x equal. So using the appropriate notation, if you use the wrong notation there, they probably would mark you down for that. So going back to this line here, in fact, we could use this most simplified form. That's probably the best option. So that's going to be 2x to the power of 4 plus 3x plus the c value, which is 4. So that's the solution for that one. Moving on to the next question. This is an exponential logarithm question. In part A of the question, they just want us to sub in a value. That's why it's quite a low marked question. I think it was just 1 mark. So they're telling us that in this part A, the time value is 30. And essentially, this is really just a calculator exercise. You just plug in the number in to see what you get. So the concentration of medicine, I think it was, at time 30. So you could put a 30 in there if you want, because that does represent the time value. So C sub 30 is just going to be 11e. Always got these weird decimal numbers in the power in these questions, but remember that's multiplying to that t. So it's going to be multiplying to the 30. And then it's just literally a case of chucking all that in the calculator. So I'll just check this one, which I worked out earlier. This comes out to be 9.38. So 9.38. Remember there are units in this question, so it was concentration. I think it was given in milligrams per liter, I think. So that's the answer for part A. That's the kind of easy part. That's just subbing in the number. Part B is the more sort of proper log exponential part. This is the part where we've kind of got to think a little bit. So they're telling us in the question about the number, the concentration falling below 0.66. So that's going to be what we're going to sub in for the concentration, and then we want to test the time value at which that's going to occur. So essentially they're giving us a number to plug in for the concentration, so 0.66, and then just keeping the rest of the equation the same and then trying to solve that for the t value. The thing that makes these questions, these sort of log exponential type scenarios, sort of unique is that you're solving for a value that's in the power. So the process involves getting that variable out of the power, and in this case that's where we're going to use a logarithm to base e, which is natural log, so ln e. So that's going to, just ln, which is going to be later on in the question. So we can start by simplifying. Before we use the ln, we need to get this to be just an e on its own. So we divide both sides by 11, so we get 0.66 divided by 11 equals this guy here. The next part is where you introduce the logarithm. So essentially we're taking the log to base e, so ln of both sides. You could write that in at this point, like literally put an ln there and an ln there, but the net effect of the ln on this side is just to cancel the e, essentially. You don't need to show those intermediate lines are working. You kind of should really, but you don't have to. So you can just imagine that by plonking an ln there, it's going to cancel out that e and leave you with just whatever else is in that expression, which will be this weird decimal number, so minus 0.053t. And on this side, that's going to be ln, natural log, of this fraction. Always kind of messy numbers in these questions. That's why they're almost always calculator questions. And keeping in mind that we're trying to solve for the t value. So it's just a normal equation at this point. We just need to put the t value on one side and then divide by this number. So we're going to get ln 0.66 over 11. There's no real need to put this in the calculator at any point other than the final step. Otherwise, you're just going to introduce like more messy decimal numbers. All of that divided by negative 0.0053. And when you do that, I will consult my cheat sheet, 530.8. And I think this question was in minutes. So 530.8 minutes, and that's when the concentration would fall to this level here. In the first part of this optimization question, we're asked to make the area of the shape. So you've got to kind of think about the geometry of this question. Each of these is a rectangle, and you need the dimensions of each rectangle to get the overall area. So if you were to fold the shape together, you would find that this length here, 3x, would be sort of projected onto there, and you would find that the 2x would match up with this guy here, so that length there, and also that length there. So that gives us the dimensions that we need to make the individual areas of the rectangles, then we're just going to add them together. So to get those, you really need to think about the geometry, like how this would work if you folded the shape together. So it doesn't look like it on my diagram, but it should be that that length there and that length there are the same, and that length there and that length there should be the same, but you get the idea. So working through the individual areas, remember that's just going to be the two dimensions multiplied together. So this guy here is going to be 2x times h, which is just 2hx or 2xh. This guy's going to be the same because that h is the same height on all of those, so this will also be 2xh. This is an h here, remember, as well, so this guy here would be 3hx or 3xh, and then this guy here would be the same, so 3hx. This one here is going to be 2x times 3x, so it's going to be 6x squared. We need to make the total area, so we're just going to add those all together. So we've got two of these, so you've got 2xh plus another 2xh or hx, doesn't matter which way you put the variable, so that's going to be 4hx, and then we're going to add to that these two guys, so it's going to be 6hx, and then we've got the final shape, the final rectangle, so it's going to be 6x squared. So just putting our highest power term first, so we're going to get 6x squared, adding these together, plus 4 plus 6, so it's going to be in total plus 10hx. So that's part A, part 1. It's only a 1 marker, quite a lot of work actually in that question, just for 1 mark. So that gets us the area of the shape. In part A, part 2, which is the traditional hated optimization part A question, we need to show that this formula is true for the volume. So these can be quite tricky. This one looks a little bit ugly, having the fraction in it. But the place to start here is just thinking about the fact that if you were to fold this together to make the sort of box that they're referring to in the question, that is going to be a cuboid. So if you're trying to find the volume of a cuboid, it's just the usual sort of formula, length times breadth times height. So we just need to plug in those dimensions. So if we consider that to be the length and that to be the breadth and then h to be the height, then we would get 3x. For the first part, I'm just going to use brackets to separate these. The breadth would be 2x, the height is just h, like this, so we get 6x squared h. So that's fine as a starting point, but the problem is we've got a term here which is not in the formula, so we need to get rid of that h term to change it into something that's got x's in it, and that's what makes these optimization part A, is the proof part, is quite challenging. So we're just going to sort of park that bit of work in just now. We'll come back to that. We need to work up something else. The other thing we need to work up is the area. So they've told us the area numerically is 7,200 centimeters squared, but we know that the area algebraically is this guy here. So they're both the area, so we can set them equal to each other. So we get 6x squared, 6x squared plus 10 hx is equal to 7,200, and the goal with this part, remember, is to make h the subject of this formula, so we can take the other side of the formula and then substitute it back in here to hopefully get the formula that we're trying to get to. Remember, this is the one that we're trying to get to here. So just a little bit of algebra to change the subject. So we're going to get 10 hx equals 7,200 minus 6x squared. Then dividing both sides by 10x to get it all the way to just h. Then we'll get h equals 7,200 minus 6x squared over 10x. Okay, so that's kind of like two separate streams of working. Then we need to bring those together. So essentially going back to this point, so I'm just going to sort of pull this down here. So we can now get volume equals 6x squared, and now we're going to replace our h with this term, and that's what we want because it doesn't have any h's in it, it's only got x's in it, so it's going to be 6x squared times 7,200 minus 6x squared, all of that over 10x. And it's worth at this point keeping an eye on where we're trying to get to, which is this target here. With a little bit of simplification we can get there. So one thing we could do if we were to, for example, take out that x there, which is on the denominator, and take out that square there, that would just quickly simplify it. Then we can do various things. We could multiply the 6 into the bracket. That's maybe not a bad way to do it. Or just whatever way you want to do it, basically, it's up to you at this point. So if we multiply these terms together, we're going to get 6 times 7200, that should be a 2 in there, x over 10 minus 6 times 6x cubed over 10. And then we can just take those forward. If you take that forward and perform that calculation, that times that divided by 10, you're going to get that number. If you take this one forward, you're going to get 36 over 10, which would simplify to 18 over 5. So just a calculator exercise, really, this part, and that would give you this number here, 4320x minus 18 over 5 x cubed, and that is the formula that we were looking for. Quite a challenging optimization part A question, that quite a lot of different parts, as is typical in that question type. In question 14 part B, we're trying to determine the value of x that maximizes the volume of the box. In other words, the value of x that maximizes that function, because that function represents the volume. So this is typical part B optimization, kind of like stationary points. We're going to find the optimal value by taking the derivative, setting it equal to 0, and then solving, just like you would for finding stationary points. So you could call this v of x, if you like, to use the v dash notation, or you could use dv dx, and that's for when we come to take our derivative. I'm just going to change this one. I quite like this notation, so just simply introducing that there to make it look like the normal sort of function notation. Okay, so taking our derivative, these are in differentiable form, so that one looks a little weird being the fraction, but the term itself, the x term, is in a differentiable form, so there's nothing to manipulate there before we differentiate. So just going straight into our v dash x. So the derivative of this first term is just going to be 4320. The second term we're going to multiply by the power and then reduce the power by 1, just using the power rule. So 18 times 3 is 54, just leaving that over 5x to the power of 2, so taking 1 off the power. So that is our derivative. So like stationary points, we kind of need a little sentence in here. For stationary points, it would be something like stationary points occur where f dash x is 0. For this one, we're looking for maximum volume, I think. Yeah, so maximum volume. So you should really fit it in with the question. So we could write something like for max volume, v dash x, the derivative is going to be equal to 0. So same concept, just a little sentence as to why you're setting equal to 0. So on the next line, we're going to take that derivative, so 4320 minus 54 over 5x squared, and actually set that equal to 0. So you would generate marks already for this. The rest of this question really is about solving this equation. It looks quite intimidating with these numbers, but keep in mind that it is a calculator question. So I'm just going to move these terms to different sides. So if you move that term to that side, it would become negative. And this one would be negative, so you could then just drop the negative. So whichever way you organize it, it's going to end up being this term of the x, so 54 over 5x squared equals 4320. So we could either divide both sides now by 54 over 5, or you could times by 5 and then divide by 54. Either way is fine. It's a calculator exercise. When you do that, this comes out to be, I believe, 400. So the fact that that comes out to be a nice whole number and also a square rootable number, because we're going to have to square root on the next line, that essentially tells you you've done it right. So optimization questions don't have to have whole number solutions, but they're pretty much designed to have whole numbers, and that's kind of to give you that little bit of reassurance that you're on the correct track. So we could go ahead and square root, so x is going to equal the square root of 400. Remember, when you square root, you get both the plus and the minus, so we're going to get plus and minus 20. In this question, though, x represents something that cannot be negative because it's a dimension, so we can take off the negative answer, so the answer is just going to be 20. So we've found an optimal value, x equals 20. We hope that that's going to maximize the volume of the box. But at this point, we only know it's an optimal value. We don't know if it's a maximum or a minimum. So we need to prove that it's a max, because that's what we want in this question, either by using the second derivative test, or probably for most students using a nature table, just kind of like if you were proving in a stationary point question whether a point is a max or a min value, max or min turning point. So I'm just going to set up a nature table for this one. Essentially, to some extent in optimization, you can cheat the nature table because we already have an expectation that we want it to be a maximum. So we can just kind of set up the table to make sure it's a maximum. If you use the second derivative test, you need to do it a little bit more carefully. So we're just putting in our value, which is 20. We need to choose some values to test on either side of those. So as long as you put in appropriate numbers like 10 and 30 or 19 and 21, it doesn't really matter what the numbers are, as long as they're in an appropriate place. X couldn't be, for example, negative here because it represents a dimension. That would actually probably throw the result off. So they've got to be reasonably sensible values, but any values that are in the right place. This is going to be our derivative here, so v dash x. And then this is the shape or the slope, whichever way you want to name that. So at this optimal value, which is like a stationary point, the derivative is 0. That's how we found that 20, so that's definitely going to be a 0. And then we just need to test this. Well, we kind of need to test it, but we kind of don't, right? So theoretically, we should take the 10 and the 30, put them into the derivative, and then test whether we get positive or negative. But remember in this question, we're trying to find the x value that maximizes the volume in the box. So we know that if it's a maximum, it's going to have to be a shape that looks like this rather than the other way. So that's going to have to be a plus and that's going to have to be a minus. If you did put the numbers in, like you should do really, 10 should go into here for the x and 30 should go into here for the x and work out what you get. I'm sure you would get a plus and a minus. So that nature table, or if you use a second derivative, is necessary in this question to prove that x equal to 20 doesn't just give you an optimal value, but it's a value that leads to the maximum volume. In question 15, we're asked to find the coordinates of the center point of the circle. It's a challenging little question, this. There's not a whole lot to go on. It's definitely into the realm of problem solving, but we have to be tuned into the fact that they're telling us that the point lies on the y-axis. So we definitely know that because that point lies on the y-axis, it's got an x-coordinate of 0. So that's one thing that we can write in already. It's really easy to skip over that information, but that's going to be crucial information, I'm sure, later on in the question. Otherwise, they wouldn't have put that in the question. They don't put stuff in like that just for the sake of it. You know, it's crucial information to solving. So what have we got to go on? Well, we've got a tangent line here to the circle. We're given the equation of the tangent line in the wrong format. So anytime you get a line in the wrong format, you should reformat it. So just making it into the sort of y equals mx plus c format. So subtracting x from both sides, dividing both sides by 3 to get minus 1/3 x plus 17 over 3. So quite ugly looking terms in that equation, but all we really care about is the gradient. And the reason we care about the gradient is because one of the key rules, remember, to do with circles and tangent lines is that the radius line, which would be, you know, that line there, the radius of the circle, makes a perpendicular to the tangent line. So that tells us then if we know that the gradient of our line, let me pull this up here. So the gradient, I'm just going to call this subscript t for tangent. So the gradient of the tangent line is minus 1/3. And notice, by the way, that looks quite correct based on the diagram because that's a negative gradient and it's quite shallow. That then implies, because the two lines are perpendicular, that the gradient of the radius line is going to be positive 3/1 or positive 3, so just 3. And again, just looking at the line, that's going in the positive direction for a gradient, and also 3 is quite steep, so that looks to be spot on. So what can we actually do with that? Well, what we can do is find the equation of this line, the radius, because we've got a point on the line, 0.25, and we've also got the gradient. So just using our normal straight line formula, so y minus b equals mx minus a. So plugging in our values, so our b value is 5, so y minus 5 equals our gradient 3, x minus our a value, which is 2. Then just working through the algebra, I'm just going to move this over a little. So y minus 5 equals 3x minus 6. Adding 5 to both sides, so we get y equals 3x minus 6 plus 5 is minus 1. So it's difficult to check whether that's correct or not because our diagram doesn't have like an xy grid. So otherwise, if it did, we could maybe check, for example, the y-intercept. But anyway, we don't need that because our question's not just about finding that line, it's about finding, remember, the center point. But what did we know about the center point? We knew that it had an x-coordinate of 0, and now we know that it lies on the line that's got this equation here. So if you've got half of the coordinate and you want to find the other coordinate, you can just substitute that into the line. So we're just going to substitute x equal to 0, and that's going to give us y equals 3 times 0 minus 1. So that is 0 minus 1, which is minus 1. So in other words, when the x-coordinate is 0, the y-coordinate is minus 1. So this point here is 0 minus 1. So the final answer, the center point of the circle, 0 minus 1.